Okay, so now we're going to look at some examples based on what we have learned in the previous video. If you remember, we were introduced to the equation. Let me rewrite the equation here. Whoops, sorry. Let me write the, no, not that. What am I doing? Okay, so the equation that we'll be working with for the most part in these examples is, all right, where's my pointer? Okay, something is, let me try this. Okay, so the equation is, okay, this thing is not behaving itself. Okay, so the equation is Q is equal to M times C times delta T. So this is the equation we'll be using for the examples we're about to get into. So the first question says how much heat in joules, hold on, let me get this thing working here. How much heat in joules and in kilojoules does it take to raise a temperature of 225 grams of water from 25.0 degrees to 100 degrees Celsius? All right, so what I'm going to do is get out of this and open up my writing tablet, clear this page. Okay, so as I said before, the equation we'll be using is Q is equal to M times C times delta T, right? The question is asking for Q. We are given the mass, which is 225 grams. Now, what is not given in the question is the specific heat of water. I think I showed you before, it is 4.18 joules per gram degree Celsius. So that would have to be provided for you in a normal test or exam situation. And then we get to the change in temperature. So the change in temperature would be the final temperature minus the initial temperature. So the question gives you that the temperature is raised from 25 degrees Celsius to 100.0 degrees Celsius. So it's a final temperature, 100.0 degrees Celsius, minus the initial temperature, which is 25.0 degrees Celsius. And that's basically it. All you have to do is the math from here. This part here works out to be equal to 75.0 degrees Celsius. And then we need to work out the rest. So that's 75 times 4.18 times 225. And then we round off to 3 sig figures. So according to my answer, this would be equal to 7.05 times 10 to the 4 joules. And the question is also asking for the answer in kilojoules. So we multiply this by 1 kilojoule above and 1,000 joules below, because kilo means 1,000. So let me do that calculation, divide by 1,000. So that works out to be equal to 70.5 kilojoules. 70.5 kilojoules. All right, so this particular question is, very straightforward. All right. Okay, now the next question, going back to the PowerPoint here, says what will be the final temperature if a 5.00 gram silver ring at 37.0 degrees Celsius gives off 25.0 joules of heat to its surroundings. And it says use the specific heat of silver listed in table 6.1. So if you go back to the table here, for silver, the specific heat is 0.235. So let me just make a note of that here. So the specific heat of silver is, let me just put C silver, Ag, is equal to 0.235 joules per gram degree Celsius. All right? So that is what you're going to need in addition to the other information that's given. So again, let me go back to my writing pad here. Let me get rid of that. So again, we'll be using Q is equal to M times C times delta T. Now, what the question is asking for is the final temperature. So I'm just going to say let T2 equal to the final temperature and T1 equals to the initial temperature, which means that delta T will be equal to T2 minus T1, all right? So What we need to do is find delta T from this equation here. So based on this equation, we can rewrite this as delta T is equal to Q divided by M times C. So Q is given as being equal to, now again, this is where we have to pay attention to how the question is worded. So let me go back to the PowerPoint here. If you look at the question, how it's worded, it says that it gives off 25.0 joules of heat, right? So what that means is that the Q will be minus 25.0 minus 25.0 joules of heat divided by the mass, which is equal to 5.00 grams times the specific heat, which is let me go back to this again, 0.235 joules, right that here, 0.235 joules per gram degrees Celsius. So that will be equal to delta T. And in terms of units canceling out, the joules will cancel out here and here, the grams will cancel out here and here. So your final unit would be in degrees Celsius. So let me do that calculation. So that's minus 25 divided by 5 times 0.235. So according to my calculation, this works out to be equal to minus 21.3 degrees Celsius. So delta T is equal to minus 21.3 degrees Celsius. So coming over to here, coming over to this equation here, the aim, of course, is to find out the final temperature, which is T2. So T2 would be equal to delta T plus T1. So delta T is, as we calculated here, is minus 21.3 degrees Celsius plus the initial temperature. Based on the question, the initial temperature is 27.0 degrees Celsius. So we're going to add minus 21.3 to 27. And according to my calculations, this works out to be equal to 5.7 degrees Celsius. So this would be the final answer right here. All right. Okay, so that's basically how the second example is done. All right, so let me go back to the PowerPoint here. And there's a third example coming up. Now in this example, this is dealing with the conservation, the first law of thermodynamics, which basically says that in any chemical or physical process, the amount of heat that is lost by the system is equal to the amount of heat gained by the surroundings, all right? So this is something very similar. Now, let me read the question first so that we can get a feel for what the question is asking for. The question says that a 15.5 gram sample of a metal alloy is heated to 98.9 degrees Celsius and then dropped into 25.0 grams of water in a calorimeter. The temperature of the water rises from 22.5 degrees Celsius to 25.7 degrees Celsius and is asking for you to calculate the specific heat of the alloy. All right, so let's think about what's happening here. So what we have here is a metal that is heated to a relatively high temperature, 98.9 degrees Celsius. And then it's added to water, which is cooler, right? Because the initial temperature of water is 22.5 degrees Celsius. Okay, so what's going to happen here, and I think I mentioned this earlier in this chapter, is that when you put the hotter metal and immerse it in the colder water, what will happen is that you're going to have a heat transfer from the metal to the water, right? And that heat transfer will continue until both the metal and the water are at the same temperature. And if you remember, we call that particular state a state of thermal equilibrium, all right? So the first thing I'm going to write down here is that the heat change for the metal will be equal to minus the heat change for the water. And let me change my ink because I prefer black ink. Okay, so that's the first thing I'm going to write down here, because remember I said there'll be a heat flow or heat transfer from the metal to the water. So therefore, whatever the amount of heat that is lost by the metal, the amount of heat that is gained by the water is the same. So that's why we have a minus sign here, because basically as far as the metal is concerned, it is losing heat or losing energy in the form of heat. So therefore, the change in the heat, the change in heat for the metal will be negative, while the change in heat for the water will be positive. So that's why we have a negative sign here. So the next thing I'm going to do is write down this expression. Remember this expression, Q is equal to M times C times delta T. But what I'm going to do is write down that expression for each of these terms here, for QM and for QW. So the heat change for the metal will be equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And then we get over on the right side, we put the minus sign first, and then the heat change for the water would be equal to the mass of the water times the specific heat of the water times the change in temperature of the water, all right? Now, remember the aim of this question. The question is asking for you to calculate the specific heat of the metal, the alloy. So in other words, we need to isolate this on one side of the equation. And therefore, we can achieve that by dividing both sides by the mass of the metal times the change in temperature of the metal. So we divide that by the mass of the metal times the change in temperature of the metal. So this will cancel out with this will cancel out with that. So basically, we're going to get this expression here to be equal to the specific heat of the metal. And all we have to do from here is to plug in the numbers into this expression to get what the question is asking for. However, you have to be careful because there are different terms being given here, and you have to basically make sure that each of these terms are placed in their right positions, right? So what I'm underlining now are the different numbers representing different quantities for the metal and the water, all right? So the first thing we're going to figure out is, what is the mass of the water? Well, first, can't forget this, let's put the negative sign first, then the mass of the water. According to the question, the mass of the water is 25.0 grams, so we're going to put that here first, right? Then we're going to multiply by the specific heat of water, which again has to be given. It is 4.18 joules per gram degrees Celsius. Multiplied by the change in temperature of the water. So what's the change in temperature of the water? It's the final temperature, which is the 25.7, minus the initial temperature, which is 22.5. So we're going to put that in parentheses here. It's 25.7 minus 22.5 degrees Celsius, all right? So that takes care of everything in the numerator part of this setup. And then below that, we have two things we have to figure out. The mass of the metal, which is given here, 15.5 grams. So we're going to put that down here, 15.5 grams, times the change in temperature of the metal. Now, this is where we have to be careful, because remember what I said. As far as the metal is concerned, when you add it to the water, the temperature falls from 98.9 to the same temperature, the same final temperature of the water, which is 25.7, right? So basically, in this particular case, it's going to be the final temperature, 25.7. So let me put that down here. 25.7 degrees minus the initial temperature, which is 98.9 degrees Celsius, all right? So that's basically the setup. And of course, some units will cancel out. The gram units will cancel out here and here. And degrees Celsius units will cancel out here and here. And basically, the only unit remaining would be joules per gram degrees Celsius. So basically, we just need to do the number crunching. What I would do, of course, is work out what's within the parentheses in both cases. So 25.7 minus 22.5. So this part here will give you 3.2 degrees Celsius, which will cancel out. The degree Celsius will cancel out. And then the 25.7 minus 98.9, that gives you minus, write it here, minus 73.2, all right? So now we can do the rest of the calculation. So the numerator part is 25 minus 25.0 times 4.18 times 3.2, and then divide that by 15.5, and then divide that by 73.2 minus. So the answer I got, and we'd have to round off the answer to 2 sig figs. So the answer I got is 0.29 joules per gram degree Celsius. Okay, so that's basically how we use the Q is equal to N times C times delta T. This should be C here, times delta T. That's how we use that equation to solve for the specific heat of the metal alloy in this particular question. All right, so we're going to stop here. And the next topic we're going to talk about is measuring enthalpy changes for chemical reactions. All right, so we're going to go back to some extent to our discussion about the calorimeter and how it is used to measure enthalpy changes. Okay, until next time.